So in the last two videos, we just started quantum physics. Now we're on to relativity. We've got Einstein's special relativity. That's what this whole section is about, the last section of the nature of light. And relativity and quantum physics together make up all of modern physics. Those are the foundations of modern physics right now. So this is the beginning of how Einstein came up with his theory of special relativity. And for his theory, he really just had two main assumptions he had to make. He had to make the assumption that the speed of light is a constant and that all inertial frames of reference are equivalent. Let's try and unpack that second one first. First of all, what is an inertial frame? An inertial frame is a area that is not accelerating. A frame of reference is like a point of view. So it's a point of view that isn't accelerating. So this is the surface of the Earth. Somebody standing still on the surface of the Earth, they are in an inertial frame of reference because they are not accelerating. If someone is inside a car or truck or something, and that truck is moving with a constant velocity, then they are also in an inertial frame of reference. Good for them. However, if someone is, say, falling, as they fall, their velocity is not constant. Instead, they're falling with a constant acceleration. They are not in an inertial frame of reference. Or if, again, they're inside the truck, however, the light just turned green, and so now the truck is accelerating forwards, they are again not in an inertial frame of reference. Okay, so constant velocity, whether that velocity is zero or it's some number that's constant, those are inertial, these ones not inertial. And keep in mind, I said this was the surface of the Earth, and the surface of the Earth itself is moving at something that's approximating a constant velocity. It is turning in a circle, but in any reasonable measurement that we can do at this sort of scale, it's moment to moment, it is pretty constant. Um, okay, so what do we mean by all inertial frames of reference? So these ones are all equivalent, which I guess means that these ones are not equivalent. What do we mean by that? Well, it means that in any of these places, if you do some kind of experiment or observation or measurement, you should always get the same results. In fact, you should get the same results so much that you can't even tell um, the difference between these inertial frames of reference. So if you were inside a box, which was a truck, or if you're inside a box which is just sitting on the ground, and this truck was really moving at constant velocity, okay? No bumps on the road, it's just nice, smooth, constant. You wouldn't even, and you can't see outside, you wouldn't be able to tell, right? You drop a ball, it falls straight down. It's not because you're inside a moving vehicle. If you drop a ball, it goes backwards or something. Um, if you're Another good one to think about is an airplane. Airplanes move at hundreds of meters per second, right? But they're usually moving at a pretty constant velocity, okay? And you can easily, pour yourself a cup of water and drink it. And, the fact that you are moving, the glass is moving, everything's moving at hundreds of meters per second, that's irrelevant to the fact that you can still drink your glass of water as if you were just sitting on the ground nice and still. And the ground itself is moving at a very incredibly high speed, and that doesn't stop you from doing anything in normal day-to-day life. In fact, we believe so much that we are staying still here on the surface of Earth that for a long time, people still think that the Earth is flat and that we are not moving. That's how much inertial frames of reference are equivalent. If it was a flat Earth, we wouldn't be able to tell based on experiments we can do right where we are. We can't tell the difference between a flat Earth and a round Earth. We can because, like I said, it's only approximately um, constant. There is a little bit of a difference, and we can use that um, to tell the fact that we are spinning. Okay, and so how come these ones all get the tick? Oops, I want that to be a green one, green tick. And actually, I'll give you one more example. Floating out in space. If you're floating in space, you could see the Earth rotating past. But if you were floating in space inside a inside a box. You shouldn't be able to do experiments in there that are different to the ones on Earth, assuming there is no acceleration. Okay, now what is different between these ones and our ones over here, our non-inertial frames of reference? Well, the difference is that in these ones, things are different. If you're in an accelerating car and you're trying to pour yourself a glass of water, you're going to have a really hard time. You might notice that if I don't know, your brother or your cousin or someone who drives really crazily, if they're in the driver's seat and they're at a red light and the light turns green and they hit the accelerator and your seat pushes you backwards, right? That feeling you get of being pushed backwards, that is the acceleration. That is not equivalent. Experiments you do during that time are not going to work out the same. Um, okay, so some evidence from day-to-day life of why inertial frames are equivalent, and I guess by proxy why non-inertial frames are not equivalent. But really, this equivalence is built into all of physics. Physics relies on symmetry. Any time you write a law of physics, it's only a law if it works in all situations, whether you are standing in a still room or if you're in a moving room, the laws of physics still work. F equals ma still applies. So whatever law of physics you write should be the same for all inertial frames of reference. Okay, let's think about the other one now. That is the speed of light in a vacuum is an absolute constant. Um, this is actually a weird one. People thought it wasn't a constant for a long time. They thought that light is a wave and that wave needs to have a medium, just the same as waves in an ocean have the water, waves of sound have the air. They thought light needed its own medium in order to move. And in air, if the air is moving, so say we have a wind traveling this direction and you shout into the wind, right? You make a noise, right? The velocity of the noise that you make is larger because the air it's moving through is itself moving. If you try and shout against the wind, the velocity is much smaller. It doesn't go anywhere near as fast. So they thought the same thing happened for light. They thought light had a medium. If that medium is moving, then you can make light move faster or slower if it's going with the medium or against the medium. And they did an experiment to try to measure how fast the medium of light is moving. So the medium of light they called the ether. And they said it had a few properties. They said it's invisible because, where's the ether? They said it must be everywhere because light can go everywhere, so it must be in the vacuum of space because light can travel from the sun to Earth. And they thought that, it had a bunch of other properties. And they thought that the ether was this thing, and it's everywhere. This is the ether. It's everywhere. And they thought, well, the Earth, they know. There you go, thicker thing. They know the Earth is moving through space. So the Earth is moving through space. That means this ether around it is actually streaming past the Earth like this. Just kind of like, even if the air is still, if you're riding on a bike or if you're in a car with the windows down, the wind still hits you in the face. It's not because the air is moving, it's because you're moving through the air. So they thought the same for the Earth. The Earth moving through the ether, it feels the ether wind. Okay, so on Earth, we have the ether, and the ether is moving. It's moving to one side, the opposite direction to the direction of Earth's motion. And they devised an experiment. They thought, if we set up an experiment so that we have a laser shooting out a laser beam, and that laser beam hits a special mirror, and this mirror lets some of the laser light through, like this, which hits another normal mirror. So the special thing about this middle mirror is that it lets some light through and it reflects some light. So boom, the laser comes through, it let it through. But now when the laser's bouncing back, now it's going to reflect it back like this. Okay, and that's not all. Some of the laser light that's coming through, I'm just doing a different color to help demonstrate this. Some of it doesn't pass through, some of it actually reflects off. hits a mirror up here, then comes down, and now it passes through here. Okay, and these two beams, these two laser beams, they should have some kind of phase difference, kind of like our diffraction patterns. One wavelength might be a bit ahead or behind the other, and they should create a diffraction pattern, or I'm sorry, not a diffraction pattern, an interference pattern based on how they line up. So we might have, wave one like this, and wave two might be, slightly ahead of it or behind it or whatever, and that's going to create some kind of overall interference pattern, which might look something like, it might look something like that. I don't know. Anyway, either way, you get some kind of pattern. It ends up looking like bands of light. So where the peaks are, we get some high bands of light, etc. Now, what they did then, and they thought that this red light, because it has to travel against the movement of the ether to go back, it would take longer time to travel. So that's why the orange one is ahead, because the orange one is moving perpendicular to the movement of the ether. So it should actually be able to go faster than this red one, which has to move against the ether for half of its journey. Okay, it's just like if you're caught in a rip, like the current of water pulling you back, don't try and swim against it, you swim across from it. Okay. So then they thought they get this whole thing and they rotate it 90 degrees. So rotate, rotate, rotate. Now that they've rotated it, the ether wind should now be going the other direction, right? Once they've rotated it, this ether wind should be helping the red one, well, not helping, but it should be hindering the orange one more than the red one. Okay, so by rotating it, the ether wind's now in a different spot. Let's see if I get this right. If they rotate it in that direction and the wind was this way, now the wind should be going, towards the orange like this. So I think our ether wind now is up like this. It's either up like this or it's down, I'm not sure. But now the orange light has to move against the ether wind and the red light is moving perpendicular to the ether wind. So now down here, the red should be ahead and the orange should be behind, and we should get a different interference pattern because of this. What did we find out? We found out that there was no difference. Or the difference that was measured was within the measurement error of this device. And they did this over and over again. They made it more and more accurate. And in the end, they concluded that light travels at the same speed, no matter which direction it's going. And from that, they concluded that there was no ether. The ether does not exist. Let me emphasize that. Ether does not exist. If the ether doesn't exist, that means light doesn't have a medium. Okay, light has no medium and it has no mass. What does that mean? Well, any object that has no mass, if you want to work out how fast it will accelerate, you're essentially going to be dividing by 0 if mass is 0. So light doesn't actually accelerate. Light, when it's created, is immediately going at the maximum speed possible in the universe. And that is the speed of light, 300 million meters per second. Now this has some really crazy consequences if you start to think about some really strange situations. Let's try and get into them now. So if, like Einstein, we believe that these two principles are true, then we start to run into some problems which seem really, really crazy. Let's think about one of them. One of Einstein's famous thought experiments, which is a train that's moving at c, the speed of light. Yeah, 3 times 10 to the 8 meters per second. That's its velocity. And he imagined that there's someone inside and they're trying to look in a mirror. And there's someone outside, and The outside person is looking at this person looking at their own reflection. So here's the thing. Okay, so if this person's to look at their own reflection, that means light must travel away from them, hit the mirror, and then bounce back so that they can see themselves, right? That makes sense. And this person outside, if they can watch this light, they can watch the light travel away from the person and bounce back. If it makes it easier for you, you could imagine that this person is holding a laser, which the outside observer can more easily see. Or maybe they've got lasers for eyes, and so their laser eyes are shooting in the mirror and shooting back. Either way, here's part of the conundrum. This outside person watching, they are seeing this light travel away from the person at c, the speed of light, right? Because it is light. The red beam here is light. Light always travels at the speed of light. However, the person themselves is going sideways at the speed of light. So really this outside person, from their point of view, compared to them, this light should be traveling at 2 times the speed of light, okay? Because the person's traveling at the speed of light and the light coming out of their laser eyes is also traveling at the speed of light. Speed of light plus speed of light equals 2 times the speed of light. Okay, but the person inside, they just see the light go away from them at normal c, speed of light. So we've kind of broken both of these rules. One, the speed of light in a vacuum is an absolute constant. No, it isn't, because from this person's point of view, it's 2 times the speed of light. From the inside person's point of view, it's just 1 side the speed of light. Also, all inertial frames of reference are equivalent. Oh, that part we're okay at the moment. Because for that part, the person inside, they see the light traveling away from them at the speed of light. This person, if they had laser beam eyes, they would see their light travel at the speed of light. So everything's constant. Okay, so if we say that this first rule has to be correct and the speed of light in a vacuum is an absolute constant, that means this outside person cannot see it traveling at 2 times the speed of light. That means they must see it travel at just the normal speed of light, which means the laser light coming away from this person should never be able to catch up with the mirror, because the mirror is moving away at the speed of light and the light's moving towards it at the speed of light. So that light never reaches the mirror. They both just move away from each other at the same speed. Which means the person inside the train doesn't get to see their own reflection. The light going away from them never reaches the mirror. Now we're breaking the second assumption here. All inertial frames of reference are equivalent, meaning there's no experiment you can do inside an inertial frame of reference which tells you what your speed is. The person inside here, they just need to hold up a mirror. If they don't see their reflection, they know they're traveling at the speed of light. That is definitely breaking the law of relativity here. Einstein thought about this, he had a problem. Either light traveled faster than light speed from the outside person's point of view, which breaks the first assumption, or the person can't see their own reflection, which breaks the second assumption. This was an issue he could not resolve for a long time. He eventually came up with an idea which worked. That idea seemed a bit crazy. He said, well, hang on, we're making some other assumptions when we're thinking about this problem. Some other assumptions which maybe we don't need to make. Here's one of those assumptions. We're assuming that both people measure this distance to be the same distance. And we're assuming that both people measure time inside the train to be going at the same time. Now we have a solid assumption, a solid law based on evidence saying that the speed of light must be consistent for both people. But we don't have one of those assumptions to say that distance or time need to be the same for both people. So instead of changing the speed of light, instead of saying the outside person sees 2 times the speed of light while the inside person sees 1 time the speed of light, instead of saying that part changes, let's instead say that distance and time are what's really changing. And he turned out to be correct. That is what actually changes. Just so you know, This outside person, when they're looking inside the train, they see time time travels much more slowly. If they look at their own watch and they look at the clock inside the train, their watch will tick by faster than the train's watch. Also, if this train moved past for a long time, they would see themselves get older faster than the person inside the train. Also, as the train is going at the speed of light, the distances inside the train actually contracts to nothing really at the speed of light. But the person inside the train doesn't see these effects. They see their own time passing normally. They see their own lengths happening normally as well. Sounds really crazy. Remember that this only happens at the speed of light or at speeds very close to it. That's when these effects are noticeable. Um, Next video, I'm going to go into some of the evidence that we've got that shows time slowing down, distances contracting, and there's some other effects as well that are related to this. Okay, that's special relativity.